Okay, we're back, and I wanted to do a rotations example here, where you have both linear and rotational motion in a system. And this is the picture that we're looking at. It's kind of more of a lab-based problem, where we want to try and figure out from this particular setup. We're kind of forced to use this experimental setup here in order to determine the moment of inertia of this contraption. Okay, so imagine this might be like PVC pipe or something from the hardware store, where you've got this central pole right here, and then you have this kind of L or T-shaped setup with the plastic tubes. We have a hanging mass over a little pulley that's whose string is wrapped around that central post right there in the center. Okay, so presumably this hanging weight is heavy enough. When you release it from rest, it'll start to fall. It'll start to accelerate straight down. And that linear motion of the hanging mass causes the contraption to spin. Okay. And so one assumption that we can make up front is that as long as this hanging mass is falling straight down and accelerating, it'll be a constant acceleration. Okay. So think about the concepts here. Our goal is to try to find the I, the moment of inertia or rotational inertia of this apparatus. It's going to spin, it's going to accelerate. It starts at rest and it's going to start going faster and faster as the hanging weight falls. Ask yourself why. Okay, fundamentally, what makes something spin in the first place? Well, the answer would be torque. What force is creating torque on this thing? Well, the only applied force is going to be the tension in the string. Okay, not the weight out here necessarily, but a consequence of that hanging weight is the tension in the string. That's the physical force being applied to this apparatus that we have to consider. Okay. How is torque related to I and the angular acceleration? Well, that's a Newton's law thing, right? It's instead of F equals ma, for rotational motion, we've got torque equals I alpha. So that kind of, if you think it through like that, we can identify things we can measure. Can we get some value of forces and torques? Can we measure that? Can we find an acceleration value, alpha or angular acceleration value for this thing? If we can do that, we can solve for I. We don't know the mass of this thing, so we're not going to be able to measure or determine it directly. We're going to have to calculate it. In fact, the way these lab-based problems are set up, if you kind of take a peek at these different questions being asked, they want us to tell them what can we measure, what quantities are we going to use to make a graph. We want actually to get the I value from the graph, okay, presumably some straight line, and then describe how we do it. Okay. So some of the things that we can define here, the things we can actually measure, well, we can measure the height, like how far this hanging mass is going to fall. We can time it. Okay, and if it's a constant acceleration, if we know time and distance that you fall, we've got kinematics equations where we can get the linear acceleration from this. My claim is, if we can find the linear acceleration of the hanging mass, we can find everything about the motion of the system. Let's kind of walk through how you do that. Okay, so first thing is, ultimately what we're after is a graph. If we think in terms of torque equals I alpha, well, that implies that the moment of inertia that we're trying to find is torque divided by an angular acceleration. That alone sets up what the graph should be. So if we want a straight line, if we want to get a slope that gives you the moment of inertia's value, slope is rise over run. So if we can get some data points, some different torques and different accelerations, the rise would be the torque value. If the run or the x-axis is your angular acceleration, measurements should give us a best fit line through this. And the slope of this graph should be that moment of inertia. Okay. So first things first, the main thing we can measure is the height and time, how long it takes for that thing to fall. So what's the linear acceleration of the hanging mass? Well, I seem to remember in kinematics, if something falls, and we know the time, the distance that you fall is 1/2 AT squared. Okay, so by measuring the time and height, we can get a value of A, the linear acceleration. It's 2 times the height over the over the fall time squared. Excuse me. Okay, so those are some measurements we can actually make. Now, alpha, okay, that represents the angular acceleration of our contraption. Well, that string is wrapped around tightly around that post, and as long as, if we assume that there's no slipping between the post and the string, there's this relationship here between linear and angular accelerations on things that are rotating, where the proportionality constant is the radius of that little tube up there, that little r. So we can get an alpha value. Okay. That's the alpha value that we need for our graph. Okay, that's the angular acceleration of our contraption. We're using that little r because that's physically where the string is attached and where the tension force is creating torque on that central post. Well, how do we get the torque? How do we get the tension force? Well, we can go back to the hanging mass as it falls. If we think of the force diagram, all that's happening to the hanging weight is gravity's pulling it down, but it's being slowed down by whatever the tension in the string is. Okay. Well, we could go ahead and do F equals ma, because if the acceleration is down, okay, that means that the gravity has to be bigger than the tension. Well, we know little g is 9.8. We figure out what the linear acceleration is, okay, by measuring the height and the time to fall. And now we've got an expression for the tension force. Okay, it's the weight of the object minus the mass of the object times the linear acceleration. Okay, that gives us tension. Now we can go ahead and figure out the torque on that central rod. Torque is the force making the thing spin multiplied by the radius around the axis of rotation. Okay, with respect to that, that's the little r. That's the radius of that central vertical post where the tension's being applied. And then the sine of an angle. Well, the tension is coming off tangentially to the post. So it's a 90-degree angle between the tension force, the string, and that radius line. Okay, so this is how we do it. This is how we set it up. We know the tension value once we know that linear acceleration, and we've used Newton's laws. So we could go ahead and make a table of all this stuff. Where we could, we've got these torque values based on our measurements, and we have the alpha values based on measurements. We'll have some number of points there. We can make this graph, and the slope of that graph will be the moment of inertia of that contraption. This one's a little bit more involved because there's a few in-between steps, but remember that we're just using the basics. If you can identify that you have an accelerating system, what concepts fall into acceleration? Well, it's Newton's laws. It's kinematics. That's all we're doing here. The trick is to be able to identify that in order to find all the pieces we need to fit together. Okay, so it's kind of like backwards thinking. We're after moment of inertia. That's related to torque and alpha. So what measurements do we need to find torque and the angular acceleration? That determines the experiment that you set up. Okay. Now, if we go back and look at some of the other questions they have, we've just basically answered most of this here. Okay, we've described the experiment, the measurements we need, what we're going to do with the measurements, how to make the graph and get the experimental result for that rotational inertia. They do have one question down here, though, which is kind of interesting. When you do this in reality and you do your best fit line, maybe it has a y-intercept. Okay, and that they're kind of asking about that here. In fact, they kind of hint at how you should have done this. You have a graph of torque versus angular acceleration. What would a y-intercept mean? What could be how would you interpret that physically? Well, if you think about the nature of this graph, okay, let me erase this. Let me exaggerate this a little bit. Okay, so what if your graph did something like this, and you had this y-intercept over there? Well, that's telling you that by hanging light weights on there, okay, there is this possibility where you could add, like, hang a really small weight on that string, let go of it, and it doesn't move. Okay, so you have to keep hanging slightly heavier and heavier weights, bigger and bigger masses, until you find something that'll actually make the system move. Well, why doesn't it move right away, even with the slightest little pull? Okay, what could cause that physically? Usually, and usually things we ignore a lot, especially in first-year physics and in labs and stuff, to try to simplify the problem. One of the things we usually neglect, or say it's so small we don't worry about it, is friction. Okay, there's friction in the pulley. There's friction in trying to make that little post over there spin. Okay, there's internal friction there, and so yeah, you have to pull on it a little bit before it'll get going. That's probably what that y-intercept would represent. You need bigger weights in order to get the thing moving in the first place, to overcome any torque that internal friction is producing in the system. Okay, and that's going to be a case in any real thing. You actually will have friction involved. So that would be a really good, legitimate answer to that question. Okay, so I hope this helps. This is pretty typical of lab-based problems. We're usually looking for graphs, which means you have to find a little expression from basic ideas, where the slope of that graph will tell you the result that you're after. Okay, and so in this case, we've got some kinematics and some rotational dynamics, Newton's laws that we have to use, but it's doable once we think it through. Okay, so until next time, we will see you later.